short video, we're going to prove perhaps one of the most famous basic results of complex analysis, namely Euler's formula. Euler's formula is a relationship between the exponential function and the cosine and sine functions. And it's very surprising because we don't expect such a relationship between such functions that are so very different. It's usually stated for theta. Usually we say e to the I theta is cos theta plus I sine theta, where theta is a real valued angle. And that works, of course, but it's actually true for all z in the complex plane. So I thought I would just state it right off the bat for all z in the complex plane. E to the I z is cos z plus I sine z. This is supposed to remind you of the function cis, and if I had a theta in here, this would be our definition cis of theta. So let's get started on this formula. The proof is very easy so long as you have all the machinery in place. The main machinery is our ability to manipulate these infinite sums and products, with these power series rather. So let's just calculate e to the z. So e to the iz. So e to the iz is 1 plus iz squared over 2 factorial plus iz cubed over 3 factorial plus iz to the 4th over 4 factorial, etc. iz to the 5th over 5 factorial plus iz to the 6th over 6 factorial, etc. So that's what happens when you plug in iz for z in the definition of e to the z, which is given here. Now, the i's factor out and we get powers of I, right? Here we split this and we get I cubed, z cubed. And here we get I to the 4th, z to the 4th, and here we get I to the 5th, z to the 5th. Now, the important thing to remember about the powers of I, so we have I squared, of course, is minus 1. I cubed is therefore minus I. And I to the 4th is I squared squared, which is 1. And so once we get I to the 4th, then we just have a 1. And once we get I to the 5th, then we just begin again with the I. So this thing simplifies by factoring out the i's and then calculating the powers of I. This is 1 plus iz plus, and then this becomes, well, that becomes minus z squared over 2 factorial. So the I squared became the minus sign. And then this becomes minus I, so that becomes, again, minus I, and then we get z cubed over 3 factorial. And then this becomes I to the 4th, which is just 1, so I don't even have to write anything involving I. And then this becomes, again, plus I z to the 5th over 5 factorial. And then this I to the 6th becomes a simple minus sign, so that's minus z to the 6th over 6 factorial. And then I get I to the 7th, so that's minus I z to the 7th over 7 factorial, etc. And the next term, actually the next term is somewhat interesting. The next term is I to the 8th, which just gives us 1, and I'm back to just writing z to the 8th over 8 factorial, and etc. Now, here we have an interleaved power series. Half the terms are pure imaginary and half the terms are pure real. Now, here I'd like to split the power series. And I want to justify that because it really does need justification. It's a reorganization of an infinite sum as the sum of 2 infinite sums. And this can be potentially wrong, right? Simply consider the infinite sum 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. That is 0 plus 0 plus 0 plus 0. But if you reorganize it, then you get bad things happening. So the reorganization of an infinite sum into the sum of 2 infinite sums is potentially dangerous. But we do actually have justification for it. So I'm going to reorganize first and then explain why this is actually safe. So I'm going to reorganize this. What I'm going to do is I'm just going to group all of the terms that involve an I, that don't involve an I, all the real terms, and then group all the terms that do. So this is going to be 1 plus z squared over 2 factorial, minus, and then plus z to the 4th over 4 factorial, minus z to the 6th over 6 factorial, plus z to the 8th over 8 factorial, etc. So that's the first infinite sum. And then plus, I'm going to get, I won't factor out the I yet. So iz minus I z cubed over 3 factorial plus I z to the 5th over 5 factorial minus I z to the 7th over 7 factorial, etc. So do I or don't I have permission to split this infinite sum into the sum of two infinite sums and assume that each one is defined? Well, yes, because first of all, I know that both of these converge. Why do I know that they converge? Because they are cosine z and sine z, right? Well, this one times I. So first of all, I know that they converge, and I also know that I prove that sum law for series, which says you may add the things term by term, right? The sum of ai plus the sum of an plus the sum of bn is the sum of the series an plus bn, and that is in a way exactly what's happened when we've gone from here to here, right? We've added the an plus bn in each case. Now it doesn't matter that bn is 0 in half the cases and an is 0 in half the cases, and so the addition was really easy. This is still an instance of the term-by-term addition of two different power series to give the combined power series. And so that's the justification for this. That is together with, we know that these things both individually converge. Why do we know that? Because that's cos z. Why do we know this one is? Because it's I sine z. So our prior knowledge of the convergence of those things, together with our prior knowledge of the permission to add an plus bn to produce the series which represents the sum, gives us the ability to split this in half this way. So that's a non-trivial step that relies on a lot of prior machinery, but everything is in place to justify it at this point. Now at this point, that one is straight up cos z. This one, I have to factor out an I. Now, again, we have the opportunity to question, can you factor out a constant? But that simply was the constant law for series. And so, yes, we can factor out the constant. So I factor out the I, and then what remains is nothing more than sine z. And that demonstrates Euler's formula. It's a quite miraculous formula, and I want to point out its significance when z is an angle, so theta. So in particular, so e to the I theta is cos theta, oops, I wrote that badly, cos theta plus I sine theta. So I want to point out the geometric significance of this when theta is an angle. Well, when theta is an angle, and we're talking about cosine and sine, we should definitely be talking about the unit circle here. So here, if theta is an angle, there's theta. Cos theta describes the x-coordinate of this point in the plane, R2. Sine theta describes the y-coordinate of this point in the plane, R2. Cos theta plus I sine theta is exactly this point because, well, in the plane C, right? So cos theta describes in R2 its x-coordinate, sine theta describes its y-coordinate, but if we think of this plane R2 as C itself, then the real part would be cos theta, and the imaginary part would be sine theta, and this point itself, as a member of the complex plane, would have a real part cos theta and an imaginary part sine theta, and so this point itself is cos theta plus I sine theta. And what Euler's formula is telling us is that e to the I theta is equal to that point. So if you take the number e, 2.71828 and change, if you take the number e and raise it to the pure imaginary I times an angle, what happens is you don't get exponential growth at all. You don't, like for large values of the angle, it doesn't even go to infinity. What happens is you get a rotational effect. It goes round and round and round and round. And for those particular values of theta, the exponential function is actually bounded. When you restrict the exponential function to the imaginary numbers, it's bounded, and it just rotates around and around and around and around here. And that is a miraculous synthesis of what we know about trigonometry with what we know about exponential growth. This is the same this is the exponential function, just restricted to pure imaginary inputs. And on pure imaginary inputs, we get rotational behavior. And on pure real inputs, we get growth to infinity exponential growth behavior. And that's not even the whole story, right? Because this thing can be raised to any complex value too, in which case we get a combination of these effects. We get a combination of a rotational effect plus an exponential growth effect. And so that's a little bit of a hint at the true story of what's really going on with the exponential function.